Welcome back to college. This is Real Analysis. My name is Professor Stecker, and I'm happy to be doing Real Analysis this semester. It's a shame to meet by Zoom like this. I'm sorry we had to do this, especially on the first day, but we'll be in person on the other days. I have two kids in the public school, and they have to do this remote thing, so it's best for me to be home on every Tuesday. So I apologize. That's how it has to be. But every Tuesday is going to be class by Zoom, and then Wednesday and Friday will be ordinary class in the classroom. The classrooms have to run at half capacity, but we have this class is small enough that we can all fit in the room, so that's not any problem for us. All right. I hope you're all excited about doing Real Analysis. Let's talk a little bit about the course then. So I have the syllabus. I got it all printed out right here, but I know I'm going to give it to you on paper tomorrow, but I thought we could start off going through the syllabus a little bit. I am going to share with you on my screen, if I can. I'm not a Zoom expert, not just yet at least. Actually, I would like to direct you all to the class website, which I'm not going to use Blackboard for this class because I have my own web server and I'm not really into Blackboard. So I hope that's not too annoying to you. I'm going to put the web address in the Zoom chat, if I can. Here it comes. All right, there it is. I hope you can see that. So click on that link and you will see the class website. And I'm going to share my screen too, so we can all look at it together. All right. Okay. I'm looking off to the side because that's where my computer is. Sorry. All right, so here is the class is Real Analysis, Math 3371. That's the highest number class I've ever taught. That's because we just switched to the 4-digit codes. We used to have 3 digits for everything. 3,371. So here's some just basic information here. We meet Tuesday, Friday, 2, and on Wednesday at 3. Like I said, Tuesday will be by Zoom every time, and the other 2 days will be in class in person. My email address here is the best way for you all to contact me. I have already sent a couple emails out to the class, and that's my typical way of contacting everybody. So make sure you read your Fairfield U email, and if you want to get in touch with me, this is also the best way to do that. The textbook is there. It's called Understanding Analysis by Abbott, and it's the 2nd edition. It's a yellow book, which hopefully you won't have to pay too much for it. I wasn't able to find any copies super cheap, but it's not too expensive. My office hours are listed here. So these are times when I am ready and willing and able to talk to you about, usually, people want to talk about the homework. It's not going to happen in my office. We're not, we've been told not to meet students in person in our offices. So everything on my office hours is going to be by Zoom. And the link is here, but this is the same link which you are currently using. So every time you ever want to meet with me by Zoom, that's the link to use. Hopefully your Zoom thing will remember this in your recent connections, and you can just connect back to the same one every time. That's my plan, at least. This only works because I didn't put a password on it. Hopefully nobody's gonna come and disrupt our beautiful classroom here. So that's the Zoom. Final exam date is there, Tuesday, December 15th at 3 p.m. So put that on your calendar. Be there. All right, you can also see a link to the syllabus. There's not much on this page right now, but this is where I'm going to post the homework assignments from week to week. So you will want to go back to this at least once a week to see what the homeworks are. But for now, let's look at the syllabus. Oh, there's not too much to talk about. So really, I hope that we can get started with some content today. But we'll get started at least looking at the syllabus. So we have the same sort of basic informational stuff here. All right, let's look at the course content. This is the official description of the course from the, from the university website. I didn't write these words. It says, this course examines the set of real numbers as a complete ordered Archimedean field, R as a linear vector space equipped with inner product and norm, metrics, particularly Euclidean on R, topological concepts, continuity, connectedness, compactness, intermediate value, extreme value, monotone convergence, Bolzano, Weierstrass, and Heine-Borel theorems, convergence and uniform convergence of sequences of continuous functions, and differentiation. I don't know if any of those words mean anything to you. I'm sure some of them do, actually. You should know what, like the last few words, you should recognize continuous functions and differentiation. Those sound like words from calculus, and actually, this course is kind of about calculus, although when you're doing your homework for this class, if your friends are looking over your shoulder, it's not going to look anything like calculus to them. But the ideas behind real analysis are really the same basic ideas behind calculus, although you'll see the way in which we talk about it is going to be different. The big difference is really we're going to be a lot more technically rigorous about the things that you discuss in a typical calculus class. We're going to talk about the same things, but on a real kind of more mature. This class is for more mature audiences, I would say, than a typical calculus class. All right. Anyway, let's just look at the rest of the syllabus here. Tuesday, Zoom's days. Every Tuesday is going to be by Zoom. The other 2 days will be in person. For those of you who are not coming in person, some people are just doing everything all remote. Unfortunately, I don't have the technology to let you tune in live by Zoom to the classroom. So on the on Tuesday, everybody's going to be live by Zoom. On the other 2 days, I'm going to record what I do in the classroom and post it on YouTube very shortly afterwards. So you won't be, unfortunately, you won't be able to interact, ask questions during the class time, but you will be able to watch what I did in class, and hopefully there will be enough time during office hours or any other time for you to ask me questions if you do have questions. Yeah, somebody's got a question.
Are you going to post the lectures from Zoom as well?
Yes, so everything that happens, I'm going to record and post everything. So even the people who come to class, you'll be able to watch everything later on after the fact if you like. Yeah, and by the way, I should have said about the Zoom. I know a lot of people, a lot of professors are very particular about how they want people to present themselves on Zoom, and I don't really care about any of that. So you should mute yourself when you're not talking for technical reasons, but otherwise you can. I'll leave it to you to decide what you want to do. If you want to come to the class with no pants on, that's fine. Just maybe turn your camera off in that case. If you want to keep your camera on or off, it doesn't matter to me. I suppose I like it better if your camera's on, just because I like to see the little heads in the boxes. It's more interesting for me, but really it doesn't matter. I personally feel a little weird about seeing your roommate in the corner in the back of your room or something. That to me seems a little sketchy. So however you want to play that is totally fine with me. I will keep my video on, but you can do whatever you want. And also about the Zoom, because of my setup here, I have a camera in front of me here, but my computer is over here. And so if you do have a question, please just shout out, holla at me. If you're waving your hand, or if you click the little raise your hand button, I'm unlikely to see that just because I'm not constantly looking at my own screen. I'm looking into the camera over here. All right. Any questions about any of that so far? Yeah, I'm going to record everything, even on the Zoom. And I'm going to post it on YouTube. That means, I suppose, that if you if you ask me a question, then it may be that your voice is going to get recorded. When I post them on YouTube, I will black out all of your faces because I think that's a little sketchy also. And I don't want you all to feel like anything you do or say will be available on YouTube forever. I hope you don't mind if I won't like try to garble your voices, but I'll block out your video feeds or whatever. All right, if you have real concerns about that, please let me know, and I don't want to do anything that anybody is uncomfortable with. All right, okay, can we just keep on looking at the syllabus here? So about our exams, we're gonna have two exams during class, like two in-class midterm exams, which will be, I put the dates here, October 9 and November 13th. So put those on your calendar. It says exam makeups or rescheduling will be permitted only in extreme circumstances. So put on your calculator now. If you miss the test and have to make it up, it's a big hassle for me. So please, I would appreciate if you come on the day. I would appreciate, I mean, you got to come on the day. Okay, it says students will not use calculators on the test. This is not the kind of class where you would want to use a calculator, but let's just agree you're not going to use a calculator or anything else. Just your pencil, pen, whatever. All right, and it says the final exam will be cumulative, but the midterms will not be. So the midterms just cover whatever was right before them. The final exam will actually try and cover everything. All right, and then the homework assignments, it says the homework, they're going to be taken from the textbook, and the homework will be due roughly once per week on Wednesday, not including tomorrow, but I think we'll be able to have an assignment for next week. And it's going to be collected on gradescope.com. I don't know if you used this before, but it works pretty well for math courses. I'll say more later on about how to use Gradescope. But basically, you'll do your homework. You're going to take like a phone picture of your homework pages and then submit it on a website. And I'm going to be able to grade them on Gradescope online and send them back to you electronically also. So the idea is there will not ever be any kind of exchange from you to me of physical paper, because I don't want your dirty paper. I don't want to be infected by your homeworks. So that's how we're going to do that.
Is the homework graded on completion or legitimately graded like every problem?
Yeah, it'll be a little bit of both. So I'm not going to read specifically every problem, but it'll be sort of some of your grade, maybe like, usually I do like a third of your grade is completion, and then the other 2/3 I will look individually at 2 or 3 specific problems and give you, real grades for those problems. All right, great, thanks for the questions. Okay, here's a little deal about the online submission. Yeah, unfortunately for me to do this with the tests also, I do want to do that with the tests also. So that means when you take your test, at the end of the test, you don't hand me the paper, you take pictures of it and then submit them online. So that means you need to bring your smartphone to class. Probably all of you are gonna do that anyway. Hopefully you can bring a phone with a camera which can connect to the internet from the classroom so that you can do all of this. We can have a practice with that in person tomorrow, just to make sure that everybody is cool with the Gradescope system. I think you'll find it's pretty easy to use. All right, I hope everybody has a smartphone anyway. If that you think is going to be a technical problem for you, let me know. We can work something else out. All right, and then the grading ratios here. The homework is worth 65%, the exams are worth 35%, and the exam specifically, remember there's going to be 2 in class and then 1 the final exam. So the 2 midterms will be 10% each and the final will be 15%. All right. And then there's just a note here about office hours. So this is just saying that I hope that you all feel free to contact me during my office hours and go over, usually people just want to talk about the homeworks. It's not, this semester we've been told not to meet individually with students like in our actual offices. So when I say office hours, I mean these are times when I will be connected to my Zoom and available for anybody to connect with and ask questions about anything. And I hope that you will do that. That it's a, I, ex- I expect that any responsible student will want to come and talk to me from time to time. Certainly, if you are really doing terribly in the class, you should definitely come and talk to me about it. But even if you're doing fine and just have like little questions here or there, I absolutely would love to talk to you about it. Of course, it's never required for you to come and talk to me. If you really don't want to talk to me, that's fine. But I consider that kind of communication one-on-one to be really part of like my job as a professor. And it's more fun really than me just standing there talking to everybody, a room full of people. All right. I think that's all I had to say about the syllabus. You know, this is definitely a weird semester in terms of how we got to do things electronically and everything, but really the course is not, the format at least of the course is not going to be all that complicated. So I'm going to stop my screen sharing. All right. So does anybody have any questions about the syllabus, the any details about how the class is going to go or anything like that? No. All right, great. I think in that case, maybe we can just get it started if that's all right. I'm here in my basement film studio with my sheet of glass in front of me. I don't know if you noticed that. So hopefully this will be like, you know, just like being in real class. Like I said, I'm going to record everything, so I hope that you will, you know, take notes like you would in an ordinary class. Although you don't have to feel so much pressure to write down like every little thing that I say, because you'll be able to watch again. Hopefully, I get it right the first time around. All right, ready to get started? I don't know if you were ready, if you were expecting to get started, but I'm ready. Okay, this is real analysis, right? Real, I don't know if you got the sense from the syllabus, you know, the word real as in real numbers. This class is about the real numbers rather than the rational numbers or other kinds of other types of numbers or other things entirely. This class is about the real numbers. And a lot of the concepts are things that you're already familiar with from calculus. So I'm going to say many ideas from calculus. Can everybody see my writing here? I hope that my my video quality is good enough for you to see. Many of the ideas in this class are things that you're already familiar with from calculus, but a typical calculus class will skip over a lot of the most important details. So I'm going to say many ideas from calculus, but we'll do them in complete detail. At least as complete as we can manage, all right? Complete detail. There are things, very fundamental things, in fact, in your calculus class that your professor was likely to just kind of totally breeze over. Things which are really very important that you can sort of convince somebody that they understand, even if they really don't understand. This, I think, is kind of like, well, okay, for instance, something like this. What I'm talking about specifically is a statement like that, the definition of the limit of something. So this says the limit as x approaches 3 of f of x equals 5. We are going to talk quite a bit in this class about limits. Limits really are the basic notion that essentially all of calculus is based on. You know, when you ask someone what do you talk about in calculus, usually they say derivatives and integrals, and that is from a day-to-day perspective, you do spend most of your time just like doing the derivative over and over again, or doing the integral over and over again. But both the derivative and the integral are based on the idea of a limit. Like the definition of the derivative, if you recall, the definition which you usually don't use is the thing with like the limit as like delta x goes to 0, something, 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 some fraction. You got to do a bunch of work and then take the limit. Anyway, I'm trying to say the derivative is based on doing a limit. And the integral is also based on doing a limit. The integral is defined as like the limit of some Riemann sums. And in a calculus class, usually you talk about the limit definition of those things, like for one day, and then you learn some kind of tricks, and then you do those tricks over and over again, and you never even think about the limit. But the real notion is the limit, of course, and that's what we're really going to focus on. Now, if you took a math class, I don't actually know how in depth your calculus class went that you took here. I want to talk about what exactly this means. When I was, the first time I ever learned about limits, I learned in high school. I wasn't much of like a math prodigy, but I did take some kind of calculus class in high school where we talked about limits. And my teacher said something like, what this means is when x gets really, really close to 3, the value of f of x gets really, really close to 5. And everyone in the classroom was like, okay, yeah, I see that. It didn't really enter our minds, or at least my mind, I'll speak for myself. It didn't enter my mind that my teacher was telling me something that wasn't a real definition. What I just said, though, I want to emphasize, is not a real mathematical definition of what this means. Because when I use phrases like x is really, really close to 3, okay, first of all, the fact that I said really twice should be kind of a red flag. What does it mean x grows really close, or as x approaches really close to 3? That is not really meaningful, like technically meaningful way to say something. Like x is a number, right? Yes, x is a number. So what does it mean when you say x gets really close to 3? Like numbers don't move, right? They don't get close. That doesn't really mean anything, or at least maybe it means something, but you really got to explain more of what you're talking about. As x gets really close to 3, and then you say, then f of x gets really close to 5. All right, this I would compare to sort of this kind of language, really, really close. You know, your teacher says this to give you an impression of what this is supposed to mean, although it doesn't really explain exactly in a technical sense what this means. It just gives you some kind of impression. And for, at least for me as a high school kid, that was totally good enough. I never really thought in more depth about this, but I'm here to tell you this is, for our purposes, we're going to regard this as totally bogus, and we need a better explanation of what that means. This, I would say, is kind of like when a kid asks their parents a certain question, and the answer is something like, well, you know, son, when a mommy and a daddy love each other very much, that's how you make a baby. That is an answer which is meant in some sense to satisfy the kid and make them feel like they understand something, but actually they haven't understood anything. Maybe they feel like they've understood something, but they don't know the half of it, right? They don't really, then you're not really telling them the real story. So this right here, really, really close business, is not the whole story. It's not really even part of the story. It's meant to give you an idea, but not actually explain anything. So we're going to actually talk about the definition of the limit. That, in my opinion, is like the sort of the centerpiece of the class. The whole class is not just about limits, but I'm trying to give you an idea of the kinds of things that we're going to be talking about. I thought maybe we'd start off with just a little sort of historical background, because I think the history behind the subject is pretty interesting. I mean, I like to talk about the history behind all the math subjects, but analysis especially is interesting. Is kind of a strange, twisty-turny journey that people took to get to what we now consider to be the real ideas of mathematics. As you may know, so I would say the history of analysis, at least as far as calculus is concerned, maybe you could say starts You could say it starts a lot of places. But anyway, in the 1600s, this is when people typically say that Isaac Newton and German mathematician Leibniz, we say they created or discovered, however you want to say, calculus, right? If you ask, you know, Alexa who invented calculus, I don't know what she say, at least, but this is the typical thing people say. Isaac Newton and Leibniz, both more or less at the same time, not together, but separately, had all the same ideas at the same time. They created what we now know as calculus. But neither of them, they didn't define limits. For Newton especially, and I think Leibniz also to some degree, they were concerned with creating calculus in order to solve specific problems in science. You know, Newton mostly for like describing motion of the planet, or laws of gravitation, right? So to them, it wasn't so important to come up with real definitions for everything. They just wanted to come up with like formulas that they could use that would produce answers that seemed to be correct and consistent with scientific measurements. So for them, the question of, well, what really does limit mean? They would say, I don't care what it means. I'm trying to figure out like how the orbit of Mercury is supposed to go. And so it wasn't really their concern to give what we would now call the real definitions of the concepts they were talking about. All right. And this was fine. Nobody minded really, at least there's no evidence that anybody really cared that the basic ideas of calculus were left undefined by the creators of calculus. Another kind of milestone was in the 1810s, an Italian mathematician named Bolzano. You saw his name in the syllabus. He has his name on several different theorems and things like that. Bolzano actually was the first to write. So Bolzano wrote something like what we now consider to be the true definition of a limit. Something like the definition of a limit. Interesting fact about this though, like you might be tempted to say like, okay, then this was sort of a breakthrough in the birth of the discipline of real analysis. Not so much actually, because I would say it this way, nobody cared. Bolzano himself during his lifetime was not regarded as a serious, he wasn't like a famous mathematician. He was just sort of a working mathematician who very few people really cared about. Maybe a little bit like me. I'm a mathematician, you know, I publish research, but I'm not world famous because of my research. And I think Bolzano was kind of like that. Nowadays, we regard him as sort of a giant, but in his own time, he was never appreciated, never became famous. So he wrote something which we would consider to be like a work of brilliance, but people just weren't interested at the time for whatever reason. And then in the 1820s, another guy, Cauchy, who is a famous mathematician for other reasons, Cauchy was famous, did the same thing, came up with the same idea as Bolzano, not having been familiar with Bolzano, but just on his own. Came up with the same idea, and again, nobody cared about this. Even though Cauchy was widely respected, people read this and were like, people just were not impressed with this idea. It wasn't until the 1850s that this really sort of caught on. So in the 1850s, in the work of Weierstrass, which is a German mathematician, again, by himself, not being familiar with this other work, again, Weierstrass came up with the same idea. And this time, everybody went crazy about it. This time it was appreciated. It was like at this point, for whatever reason, finally everybody saw this work and realized like, okay, we've been missing something all along. Now we're gonna, this is like a major breakthrough, even though it had already been done decades before and nobody really cared. This is a strange story. I think of it kind of like, maybe kind of like text messages like we have today. Text messages have really, in most cases, like replaced ordinary phone calls. People communicate more often by text messages than they do by phones. But nobody seems to talk about like, when was the text message invented? Because as a piece of technology, text messages are actually less sophisticated than the telephone, right? Like it is easier to communicate electronically short messages of text. Like people have been doing that since like the telegraph machine, right? That's an easier technology to do than the telephone. So like the technology of a text message is not a breakthrough technology. The idea, there isn't even like, you can't even really say who came up with the idea first, because the idea has always existed. It's just, for whatever reason, nobody wanted to do that until recently. It's a strange thing to think about. I'm not sure why. Like, why is it in the past 20 years, everybody is into text messaging, but they weren't before? Like they could have been doing this in the 1960s, but nobody cared, and now people do care. I don't know. It's weird. It happens in math too. This kind of very strange journey to an idea which had existed for a while, but nobody really cared about it. Once people sort of sat up and noticed, though, it changed everything. The entire like history, or the entire set of ideas concerning calculus were totally rewritten in terms of Weierstrass's definition of the limits. So this was a real revolution. You could say that Weierstrass was like one of the all-time greats because he triggered this revolution. But really, these other people had already done it. It just, the time wasn't right somehow. Strange story. I think it's interesting though. Anyway, let's get down to some business. We got about 20 minutes left. Any questions about that? This is my very brief historical introduction. I'm not a real historian. I think it's interesting though to talk about where these things come from. All right, nobody's got questions. Let's talk about, I suppose this is some more history, although I want to get a little bit down to more specifics. Let's talk about the real numbers. This is more history. Let's talk about the idea of the real numbers. This is something that to modern people, I think, educated in the way that we are educated, the concept of the real numbers is not strange at all. Like I personally feel like the real numbers is a very ordinary idea. It consists of just all the numbers. What I mean by all the numbers would be, first of all the counting numbers, like 1, 2, 3, all the whole numbers, also the negative numbers, also all the fractions you can make with those numbers, and then also any other number that you can make by some kind of decimal, and not necessarily just the decimals which repeat, but any decimal which does anything. Those are the real numbers. And we learn as kids about decimals, and so I think we are typically fairly comfortable with the idea of the real numbers. It's the set of any number that you can write using any kind of decimals. The idea, though, of real numbers throughout the history of humanity has not always been obvious to people. And it's only in modern times that it seems pretty ordinary to us. But in the past, this was not obvious at all, and even in some cases, sort of controversial. There were people who disagreed about if the real numbers are even a real thing. Anyway, so where I want to go in that history, so around, say, 500 BC, this is when Pythagoras, I think that's how you spell it, Pythagoras and his buddies, they're sort of a school of mathematical, intellectuals who we now call the Pythagoreans, which would be Pythagoras and sort of all the people who were inspired by Pythagoras. They did everything in terms of geometry. This was before algebra was even invented. Algebra wasn't invented for like another 1,000 years by the Arabs. So Pythagoras and all these Greek mathematicians, they never used equations for anything. They did everything in terms of geometry, and they had all kinds of, they saw geometry as carrying all sorts of like mystical significance to them. Anyway, they liked to measure everything in terms of abstract units. Like they loved things like this, a right triangle, which has 3 units on this side and 4 units on this side, and this side ends up having 5. Can I write that? Right? This kind of thing, Pythagoras is into this. This is where like the Pythagorean theorem came from. They love this sort of thing. The idea that you could have a geometric figure and you could measure the various features of this figure, and they are all measurable in the same units. This was viewed as being somehow like cosmically or like spiritually significant. The fact that when you draw geometric figures, you can measure the sides according to the same units. This is 3, this is 4, and this is 5. And it doesn't matter if I'm talking about inches or whatever. Of course, they didn't use inches, but it doesn't matter. These are like abstract units, which the Greeks, the Pythagoreans, they love that kind of thing. And they wanted to express, so they believed this was like a basic tenet sort of their like somehow like spiritualized mathematics. They believed that all lengths are, the word we use for this now, are commensurable. This means that all lengths can be expressed as ratios of a common unit. So you could somehow choose a specific unit and measure all the lengths as just whole number multiples of that unit. All right, that's what this word commensurable means. All measurable as ratios of common units. And it doesn't matter what the unit is, the unit was just some abstract unit. All right, this is what the Pythagoreans were into. But these people who, as sort of some kind of mystical spiritual practice, believed that all geometric lengths could be measured according to the same units and ratios of the same unit, the very same people discovered that shape like this, an equilateral right triangle, not equilateral, a isosceles, right? These are the same distance. We all know today that the sides go like this, 1 and 1 and root 2. And the Pythagoreans, they knew the Pythagorean theorem, of course, and so they knew that this side had to be the square root of 2. And to them, it was a big question about how exactly can we measure this side as a ratio of this unit? If you say this side is 1 unit, then what is the ratio that this side makes with that side? And the same group of people, the Pythagoreans, they discovered that root 2 is, the word we use now is incommensurable. I just put 2 M's here, but I only wrote 1 M last time. I'm not sure how you're supposed to pronounce this. This is not a word we're going to use very often. They discovered that the square root of 2 is not any ratio of the other side, which is 1 unit. In modern terms, we would say root 2 is irrational, right? It's an irrational number. That means that the square root of 2 cannot be written as any fraction of whole numbers, right? Now, to modern people, our interpretation of this, because we've been sort of coached mathematically our whole lives, our interpretation is just that, okay, that just means root 2 is some number, but it's not a rational number, right? The universe of numbers has some which are rational and some which are not rational, and root 2 is one which is not rational. Actually, the Pythagoreans, that was not their interpretation. The Pythagoreans, their conclusion, sorry, I'm squeaking here. The Pythagoreans concluded not all lengths The Pythagoreans concluded not all lengths are numbers. When they saw this, that this thing was not possible to represent as a ratio, obviously that is a length, but they said, well, I guess that's not a number, because in their opinion, the only things that they ever cared about in terms of numbers were lengths of geometric objects. And numbers to them were just anything which could be expressed as a ratio of some common unit. And this apparently is not one of those things. So the Pythagoreans just said, I guess there are some lengths which are simply not numbers. And you can't blame them for thinking that way, but it's unfortunately kind of a dead end because this causes them to just sort of throw up their hands and say, well, that, you know, I'm done here, I guess. If that's not a number, then all I can do is sort of try to talk about something else, which is a number, right? This is a, you know, you're free to come up with whatever interpretation you want, of course, but this is a dead end as far as the mathematics goes, and it's sort of remained in that state. People for a long time knew that there was such a thing as non-rational, you know, distances on figures. It took a long time though. So the next event in the story, as I'm telling it at least, this is around 800s to 1000. This is not BC anymore. So like over 1,000 years later, people all this time knew that the square root of 2 was irrational, but it took so long for people to have the basic idea. This was done by the Arabs, who at this point in history, you know, Europe was not producing science in the way that it had before. And it wasn't going to for another several centuries. But anyway, the Arabs were doing all the big scientific mathematical work in the world was happening in like the Middle East, India, and China. But anyway, the Arabs basically invented algebra around this time, and specifically for our purposes, the Arabs believed, or they decided for themselves, that all irrationals are also numbers, all right? Which we take just for granted. But this was kind of a bold shift. The Arabs decided, okay, we have ordinary numbers, and we also have these irrationals, but they said, actually, these are all the same kind of thing. They are all, so they are all real numbers. And the Arabs were among the first to have a real opinion about, or the idea that even these other numbers, the square root of 2, for instance, could be expressed as decimals, and you could compute the digits of numbers like the square root of 2 or even pi. And the Arabs were the first to say, like, these all count as real numbers. There's not a big difference. I mean, there are differences between rationals and irrationals, but they're still all numbers. And if you group all of those numbers together, you get a thing, which we now call the real numbers, all right? This is, oh, so they are all real numbers, and this is important. We can still do arithmetic with them. So while the Greeks would say something like the square root of 2, it exists as a length, but it doesn't make any sense to think of it as a number. The Arabs said, no, no, actually, it does make sense to think of it as a number. And you can even do things like add two irrational numbers together and get an answer. Or you can multiply an irrational times another irrational. Or you can multiply a rational times an irrational. All these things, they're legal. Like these things, they should not be considered as totally different entities. They really are all part of the same family of numbers. That's the idea. They are all numbers. And this is, of course, this is the way that we think of it today. All right. How am I doing? I gotta say, it's a little weird for me to be sitting here in my basement talking. I can see some of the faces. I hope I'm doing all right. We got 5 minutes left. Let me just say a few more things for 5 more minutes, and then we will continue in person tomorrow. Nowadays, so like a fully modern viewpoint of the real numbers, which you are all familiar with, you've been like living your whole lives with this point of view. So in modern terms, you know, I'm going to use this fancy looking R for the set of real numbers. Nowadays, how people would describe the real numbers, there are different ways to describe the real numbers. I'm going to say, let's talk about just like properties of the real numbers. Sorry, this thing is still squeaking. I think I'm running out of ink in there. I'll get a better one for next time. Properties of the real numbers. So the first property, I'm going to use some fancy language. These are properties that everybody, even people who are not math majors or whatever, everybody knows these, but I'm going to use some fancy words. So first of all, R is a field. Field is a word from algebra. So if you've taken our abstract algebra course, you know that course, the way that we teach it here at least, is mostly about groups, right? A group is any set which has a multiplication operation, and it satisfies various properties. There's an inverse, there's an identity associativity. A field means any set which has two operations, an addition operation and a multiplication operation. So this is like a group, only it has two operations, and those operations satisfy various properties, just like the operation of a group satisfies a bunch of properties. So anyway, when I say field, I just mean it has plus and multiplication, which I'll write like a little x, right? You can add things and multiply them, and these obey nice properties like the distributive property and a bunch of other things, associative, commutative, etc. Right? So this is one way in which people describe fields, but there are many fields that exist, like the set of rational numbers is also a field. What else is interesting about the real numbers is that the real numbers is ordered. That is, I mean, there's such a thing as an ordering for the real numbers. Not only do they have an algebraic structure to them, that is, you can add them together, you can multiply them, but they also exist kind of on a line and they go in order, right? Contrast with, say, the set of all 2x2 matrices, for instance. You can multiply and add those, but they don't live in a line in order the way that the real numbers do. So the real numbers is also ordered. And the last, I'll say, important property in this description is that the real numbers, the set of real numbers, is complete. And this is really our first major topic for this class, because you already know these things. The completeness is the first thing that I want to talk about. Basically, and I guess I'm not going to have time to explain fully what this word complete means. I'm not going to explain completely. Complete means there are no gaps in this set of real numbers. So an example of something which is not complete would be the rational numbers, because we all know that the rational numbers, they do like live on a line, but there are all kinds of sort of holes in the line if you only consider rationals, because if you're excluding the irrationals, there are irrationals all over the place inside the real number line. And if you throw away the irrationals, you're left with just a thing which has a bunch of gaps in it. The real numbers are not like that. There are no like missing things in between any of the real numbers. That's what this completeness means, but that's something that I'll give you a real definition of that probably next time. All right, I think that's going to do for today. My clock says it's time to go. So thank you for your attention so far. If you have been paying attention, I suppose I have no way of knowing. That's the fun of it. So I will see almost all of you in person tomorrow at 3 o'clock in the classroom. If any of you do have questions about logistics or anything like that, I will hang around on the Zoom for a few more minutes if you want to stick around if you have any particular questions. Otherwise, see you tomorrow.